Well, good afternoon, everybody. And I know you've had a lot of really great lectures earlier today and yesterday. What I'm hoping to do today, and I'm the extension vet here. I don't know if they mentioned. What I'm hoping to do today is kind of give you an overview of water quality, sort of in relationship to the systems you guys are going to be building tomorrow. And so I've kind of interrelated the two during this talk. We are obviously going to have to talk a little bit of chemistry, and I know you guys are like STEM people, so hopefully that won't be too confusing, but definitely ask if you have questions. I am hoping that I included things that were sort of important, at least for the management of your systems, as well as with regard to like how you're going to teach for the students as well. So we'll see how that goes. With that said, you've probably heard enough times that really aquaculture, one of the main and key focuses, and the reason, Debbie really pushes it a lot is, and she and Eric will go over the demo with Tatiana with you, is that water quality is really pretty much the basic important thing that you really need to think about. A lot of folks kind of, put the systems together, then they've got fish and, they've got water in there, so they think that's kind of fine, but it really, you really understanding the water quality is critical to managing your system. And yes, so yeah, we do have to talk a little bit of chemistry, hopefully nothing too crazy. A lot of water quality all over the news. Obviously, red tide, hopefully you guys won't have red tides in your system, but red tide is a big issue. This upper right is just talking from the Global Aquaculture Alliance, just talking about water quality. And many of you that are in the Tampa Bay area, you probably had heard about the stingrays that died at Lowry Park Zoo in a massive failure. They had a basically gas bubble disease or supersaturation. So that is something that can happen, and can happen really quickly. This Fish and Wildlife page here just talks about DO. Low oxygen is a really common cause of fish kills in Florida. So oxygen as well in systems is really critical. And again, obviously it's really important for aquarium, as well as with aquaculture. So definitely important. Water source, I think Courtney may have talked a little bit about this, but just to kind of reiterate, if you did, we've got city water and wells and surface water systems. And depending on where you are located, I'm assuming most of you are probably going to be municipal or wells, but there are different things to consider in each group. And you guys are going to have a copy of this talk. You can kind of look at it a little bit more. And, obviously we're always going to be available to talk about it. But with city water, definitely things that are used for disinfection are pretty critical, and making sure that's removed. With wells, there's all sorts of gases or lack of gases like low oxygen, other things that can be going on in these deep wells you have to worry about. And then surface water, of course, as well as even some of the wells, things like runoff, et cetera. So there's things that you need to consider from your source water as well, not just the water that's in the system. So this is kind of like my bottom line kind of take home, and then we're going to go into a little more detail, but things that you need to worry about, obviously starting with good water and knowing what your fish, and in this case, your plants, because you guys are doing aquaponics, need. And there's a little bit of a trade-off, because I know some things plants want, fish don't want, and then there's issues as well with management of both. So you need to know your source, and you need to know kind of what your baseline parameters are. You want to keep your gases at a healthy level. Things like O2, oxygen, carbon dioxide, and nitrogen gas, among others, are some of the main ones that you really need to think about. And a lot of times you may forget one or the other. You want to maintain good temperature and pH. And I think for most of you, probably 70s to 80s in Fahrenheit for the temperatures, and pH. I put 6.5 to 8.5, but really probably with the aquaponics, for your biofilters probably prefer like a little bit above 7, so 7 to 8.5. I think the plants actually might like it a little lower. So there's a little bit of a trade-off again. And again, the nitrogen cycle we'll talk about in a lot more detail, but removing ammonia, which is produced by the fish and primarily excreted through their gills. A lot of people think it's just their feces that's breaking down, but it's really the production through their breakdown of proteins, and then excretion through the gills is where most of the ammonia is coming from. And then, of course, cleaning up all the uneaten food, et cetera, particulates. So Debbie's, I know, going to go over a lot of this with you guys in terms of the testing, but nitrogen cycle, all these parameters, you guys will have a copy of this if you to kind of go over. Those are important ones. I want to point out these two, these to start with before we go into some of the other areas. But alkalinity and hardness, people get confused quite a bit when we talk about it. And some of you may or may not be familiar with these terms already. Alkalinity, we kind of consider basically a buffer against drop in pH or against acid, essentially. So one of the things that happens in your systems over time with fish in it, and if you're feeding the fish, is that your pH will start to drift down if you're not watching it. So alkalinity helps to kind of alleviate some of that shift to a more lower pH or acid. And that includes bicarbonate. We're going to talk about bicarbonate. You guys know baking soda has sodium bicarbonate, right? So you're at least familiar with that. And the biofilter bacteria really actually need bicarbonate as well as part of their food, their carbon source. So that's another thing some folks aren't aware of. And then hardness, many of you may have water softeners, and essentially they're removing primarily calcium and magnesium. You guys know scale essentially is kind of what hardness is. So alkaline hardness, some people get confused, but alkalinity is really more buffer, including bicarbonate. Hardness is more calcium and magnesium. Salinity, we're probably not going to talk. I mean, you probably aren't going to deal with too much if you are raising plants, because usually we're not going to put a lot of salt with plants, but it is something that we would consider with fish-only type systems. Chlorine and chloramines we talked about earlier about disinfection, you'd have to remove that. Other gases, we may have things like hydrogen sulfide. You guys are familiar with kind of a rotten egg smell. That can be a problem in some wells and potentially even in some systems if they really got some areas that don't have a lot of oxygen. And then toxins or a runoff, maybe heavy metals, et cetera, other things that you may have to think about. So this is a little schematic from Ron Malone. He's a colleague of ours who was at Louisiana State University. He's an aquaculture engineer, and I like it because it kind of goes over the main things that your systems are going to include. So obviously you're going to be feeding the fish, but you've got aeration, degasification, solids capture, biofiltration, and circulation. We'll hit each of those and kind of talk about your system in relation to that, like in kind of spurts as we go through. So this is the diagram that Eric gave me. It was the latest one he had of your aquaponics system. And we'll kind of talk a little bit, again, really briefly after we go through the major functions that your system is going to go through. But you guys are going to have aquaponics, the plant fixed bed at the end, in addition to the tank. So it's a little bit different from the systems we normally work with, which are primarily fish only. So number one, you guys know, just like people, fish use oxygen and they breathe out carbon dioxide. So that's pretty important, because what that means when the carbon dioxide comes out is that that will actually add and contribute to the acid in the water. So I've got a little tank here, CO2 plus water. This is a little bit of the chemistry. Will actually produce carbonic acid. And that will, depending on pH, break down into bicarbonate as well as another acid there. And I put baking soda to remind you, baking soda is sodium bicarbonate. So you guys have heard of that term before. The other place you have heard about it is in sparkling water and sodas. You guys know that's carbonated water. And the reason it has that fizz is because it's basically filled with carbon dioxide gas. And if you kind of look at it, when you open the bottle up, the CO2 is removed, the drink goes flat. And what actually happens is the pH actually goes up because the carbon dioxide is actually lowering the pH. This is a paper from one of the American Dental Association. Some of you have probably heard, obviously, that some of these drinks are really not great for your teeth. So Pellegrino sparkling natural mineral water, pH is about 4.96. Coke Classic, you guys have probably have heard, pH is about 2.37. You guys know, again, we talked about fish happy pHs for us would be maybe 7 to 8.5. So again, with a lot of CO2 in the water, we're not going to get all the way to Coca-Cola Classic, but we may get into the 4s or 5s if you have a crash in your system and you haven't been monitoring your alkalinity, the buffer. So a little bit about that. So where does the ammonia come from? Ammonia is really critical. If you remember from maybe chemistry, we obviously eat carbohydrates, proteins, and fats. Fish will, obviously all the diets will have protein in it, and protein, when it's broken down by the fish, is broken, as well as people, is broken down into amino acids and ammonia. Ammonia in our blood, or in our bodies, goes through our blood, goes to our liver, and will become urea. If you guys are familiar with urea we put into our bladders and we kind of pee out. Fish don't really want it or need to do that because they're in water. And so instead of making urea, they will release that ammonia through their gills. So one thing that Carlos, you guys saw here earlier, he kind of decided, and he's right. I mean, ammonia is kind of like fish pee, if you think about it. They're essentially getting rid of their ammonia through their gills. And when Debbie talks about total ammonia, it is actually comprised of two different components, what we call UIA or unionized ammonia and IA or ionized ammonia. So the UIA is NH3, if you guys are familiar with that chemical formula, and it is considered the more toxic form of ammonia. And then the ionized, which is NH4 plus, is considered less toxic. We still think both of them are toxic, consider them both to be toxic, but the unionized is considered more toxic. And the reason we say total ammonia is because the amount of each is going to vary depending on pH, primarily pH and temperature of the water. So you might have a total ammonia of, let's say, in a bad system, maybe 3 milligrams per liter. If a pH is low, you're going to have one amount of the unionized ammonia. If the pH is high, it's going to be another amount. So it's really proportional to pH and temperature. I forgot about this. Had this little feeding and ammonia coming out. Sorry, a little delayed there. All right, so this was my little thing to show you. As pH decreases or becomes more acidic, you have more of the ionized, which is the less toxic ammonia, okay? And so by converse, as the pH increases, you're gonna have more of the unionized ammonia, okay? So that means the higher the pH, given the same amount of total ammonia, you're gonna have more toxic ammonia in the water, or the more toxic ammonia. Now with temperature, it's also similar. You've got reduced temperature means that you're gonna have more of the ionized or the less toxic ammonia in the water. And similarly, as the temperature increases, you're gonna have more of the toxic or unionized ammonia. Okay, so you see there is a kind of similar relationship. As you increase temperature or increase pH, you have more toxicity or more toxic ammonia in the water. So we have kind of some rough guidelines that we use through some experts in the field. And basically, if you have an unionized of about 1 part per million, which is pretty high, and we consider that kind of lethal in general. And then you can see as low as 0.05 milligrams per liter, which is a part per million, that can still be considered sublethal if it's extended, can cause a lot of damage to the fish. So ideally, we want 0, basically. This is just to show you, and we're not going to go into too much detail. This is a lot of numbers, I know, but what I want you to look at is going across from the left to the right at this temperature. What do you notice about the numbers? What's happening to the numbers? Are they getting bigger or smaller? They're getting bigger, right? So again, as the pH goes up, the fraction of the more toxic ammonia goes up. And then the same with the temperature as you go down. You can see that 0.004 to 0.008. As the temperature increases, you've got a greater fraction of the more toxic ammonia. So that's, again, just to remind you about that. And yeah, don't worry about this. I did a total ammonia of 3 is very high in general for us. But if you're cycling your system, we'll talk more about that shortly. You may have a ammonia that high. And I just did a quick comparison here, did the math, because you use this chart to determine how much of your ammonia is the unionized form by using the, your pH and your temperature. So you can see that a pH of 6, using the same temperature of 77, you've got 0.0018. Sorry, I'm not using this thing. And then if you look on the right, at a pH of 8, you can see it's 0.1614 of the more toxic or unionized. So you can see there is a major difference as you increase your pH with the amount of the unionized or more toxic ammonia. And again, using our kind of little numbers, sort of our baseline numbers, you can see that 0.164 is a lot bigger than 0.05, which we consider sublethal or pretty bad to begin with. All right, so how do we get rid of this ammonia? How many of you have had aquaria before or raised fish in aquaria? Okay, so some of you are maybe familiar with this already. So there's a couple ways. The main way we're normally going to be talking about is 2 different groups of biofilter bacteria. So you've got one of your filters, we'll talk about the bubble bead filter, is the biofilter, or is the main biofilter, and that has 2 different groups of bacteria that will break down ammonia into nitrite and then eventually to nitrate at the end. So that's part of the nitrogen cycle we'll cover. But because you're using aquaponics, you also have plants which will use ammonia as well as nitrate. So again, that's something we normally don't cover because we're normally talking about fish-only systems. So this is most of the nitrogen cycle. We talked about fish being fed, that food gets broken down to protein into ammonia and amino acids, but the ammonia is excreted. They also make fish waste, and that fish waste, their feces will break down by bacteria and also become ammonia as well. So you've got ammonia, uneaten waste. Ammonia in general is bad because it does cause chemical damage to the fish inside and out. So it is a problem. But because you have plants, they will also absorb ammonia if your plants are cycling through or part of the system. So what happens in our biofilter, in the bead filter, we'll show you later, is that you've got the first group of bacteria. We call them AOBs, or ammonia oxidizing bacteria, because there's a lot of them. There's different species of them that will actually do this work. And this first group, over time, is going to have to kind of get enough of them in number to start breaking down all the ammonia that the fish are making. So again, if you remember from maybe some of your biology, you've got one bacteria, it's got to split into two become four. So it takes a little bit of time for these bacteria to get high enough in number for them to be able to handle the ammonia that's being produced by the fish. So you've got this first group that are going to take the ammonia, basically eat it, and then make nitrite. In order to do that, as I mentioned, the bacteria do need bicarbonate. They need part of that buffer because it's their carbon source, and they also need oxygen. So again, bacteria as well as fish need oxygen. That's another reason that you have to have good oxygen in your water. The nitrite, which is made by this first group, will bind to the red blood cells in the fish and keep them from using oxygen. That's why nitrite is also bad, but it is part of the process. And so when we're talking about cycling your tank, you're going to have different periods when the first group of bacteria are working, but the next group we're talking about are not working yet, and you may have high nitrite. So that's another really reason to measure nitrite. After nitrite starts going into the water and into the system, you have a second group of biofilter bacteria that we call the NOBs, or the nitrite oxidizing bacteria. Those bacteria then are going to take that nitrite, which remember we said is going to be bad because it will bind up the red blood cells and keep the fish from using oxygen. And they're going to transform that nitrite into nitrate. Nitrate is considered a lot less toxic in general for fish. Really, really high concentrations can be a problem. It may be an issue with invertebrates, but in your systems, it's probably not going to be as bad, definitely, as ammonia or nitrite. So that's kind of our end goal for a lot of the systems. The nice thing, though, in your systems is that plants will also use nitrate. So you've got the plants helping out with part of the system, which normally doesn't occur with a fish-only system. Again, these bacteria also need that alkalinity, their bicarbonate, as well as oxygen. Now you're going to start having more and more of this nitrate building up over time. There's other bacteria that really need a lot different conditions in order to take care of that, but normally the nitrate is removed by water changes or the plants in your case. So hopefully that nitrate will also not get really, really high. Again, ammonia and nitrite are toxic, and they're the kind of beginning parts of this nitrogen cycle. The nitrate is much, much, much less toxic to fish in general, but at very high levels can be a problem. So this is basically what we're talking about. This is biofilter cycling, and if you have a new aquarium and you start maybe putting one fish in there and it starts producing ammonia while you're feeding it, this is sort of what happens over time. You've got in the blue, that's kind of your first group of bacteria, the AOBs, the ammonia oxidizing bacteria. They have to build up high enough in number to handle all the ammonia that's being produced, and then they'll start declining. The ammonia levels would decline. As the nitrite levels rise, that second group of bacteria, the nitrite oxidizing bacteria, are also going to start increasing in number, and they'll start using the nitrite up, and then that will decline hopefully to zero in your system. And you can see the red line is essentially nitrate starting to increase. And luckily, because if many of you are going to use plants or aquaponics, the plants will also use that nitrate, as well as helping by removing ammonia, and that will kind of keep your nitrate levels from getting too high too. It can take several weeks. This particular chart has maybe 5 weeks, but it really kind of depends on how you start this cycle. There's a couple ways to do. You can start with seasoned media. So if there's a clean system somewhere, I'm not sure how these guys are going to have you do it, that has bacteria in it that are already doing this work, you might be able to use some of that media or that water, and that may help to jumpstart your numbers of bacteria. There are also places you can buy the bacteria that you have to store in the refrigerator, but there are a couple places that do have really, really good bacteria that you can use. But again, it's always a good idea to start with a small number of fish because you don't want to have too much ammonia or nitrite in your system at any time. So we talked a little bit about protein already and what happens when they eat protein and make ammonia. So aeration, that should be pretty obvious. You want to keep your oxygen levels ideally as high as possible. And normally we're talking about saturation, which means as much oxygen as the water at that temperature and pressure can hold. So I believe I was told you guys are going to be using some type of air stones and a pump. Degasification. Now, how many of you are familiar with that term or have heard of it? Okay, a few of you. So if you think about it, you kind of look at it, de-gas kind of means get rid of gases, right? So it's sort of kind of that to a degree, but what it actually means is it's a different type of unit that will remove the carbon dioxide. We talked about CO2 kind of being something that may not be, is really not good for your fish. You open up a Coke bottle or a Coke can and the CO2 actually comes out and becomes flat, right? The Coke becomes flat. So what this does is kind of do the same, but makes it happen a lot faster. It helps to remove that carbon dioxide from the water much more quickly. CO2, again, is not only bad because it may drop the pH that you don't want, or to a level you don't want, but it may also, will also impede the respiration, the breathing of your fish. So there are problems with CO2. And then things like nitrogen gas, which we talked about, if you remember I talked about the stingrays at the Lowry Park Zoo. They died because there was too much nitrogen gas in the system, which was a mechanical failure. The nitrogen gas got too high in the water. We'll talk a little bit about that. And it essentially ended up becoming bubbles in the blood of the stingrays and killed them. So definitely have to be always aware of that. So this is kind of what a degassing unit can look like. I believe you may not have these when you build tomorrow, but I think Eric said that's something commonly that the students can build, and he'll talk to you about tomorrow. Supersaturation, we talked about nitrogen gas. Any of you divers at all, scuba divers, or know people that scuba dive? So you're probably familiar with the bends, and it's a really similar kind of principle. So when we talk about supersaturation in aquaculture systems, essentially it's very similar to the bends and divers. So saturation means kind of how much stuff is in something. So when we talk about things like a gas, 100% saturation means how much gas can a body of water hold at a certain temperature and pressure. So depending on the temperature, it's going to be able to have either more or less gas. And the amount that's not going to be typically too much of a problem is 100%. When we talk about supersaturated, that means over 100%. That means more than the water should be holding normally. And when we talk about supersaturation with nitrogen gas, that means it's going to be really high pressure. And if it's in there, it's not normal. It's something's wrong. And once the gas may get into the fish, it's going to want to come out to become normal. And so that's where bubbles kind of come out into fish. So that's kind of what supersaturation means in general. So just again, it's sort of as a picture to remind you, first, I guess at the top, we've got nitrogen gas. Some of you probably remember this or maybe even teach this. You know, air is primarily nitrogen gas, but of course, people don't use nitrogen gas. You know, we're using the oxygen, which is about 21%. So if you can imagine air under pressure in water and nitrogen gas being a primary component of the air, you can see why, if it's not a natural situation, that it's going to be a problem for the fish. There are other things, again, argon and carbon dioxide are considered the next two, but nitrogen gas and oxygen are the main components of air. So when you're a diver, you go down, the bubbles and the nitrogen gas are kind of under pressure. They can more easily get into your bloodstream. As you rise, the bubbles get bigger, and then they start kind of wanting to come out of the blood and essentially act like little stoppers in your blood vessels, like they would in fish, and keep the blood from moving. So a little bit of that, the body can't use nitrogen gas. The body can, and there's actually potentials for supersaturation with oxygen as well, but our cells actually use oxygen. So it is a less of an issue than nitrogen gas because our body can't use nitrogen gas in metabolism. So when we talk about supersaturation fish, again, the fish can use oxygen, they can't use nitrogen gas. Nitrogen gas will essentially, when it comes out of solution in the fish, if it's under pressure, it'll kind of get into the fish. And then when it wants to kind of become at normal pressure, it'll form these bubbles in vessels of the fish, block blood, block other things going on. And even as you can see in some of the pictures that I borrowed, these bubbles will actually form on the skin, gills, eyes, etc., because they're trying to get out of the fish's body because they want to be back at a normal pressure. Many times I put in the middle, this is caused by problems with the pump. If you guys have a pump that's sucking air, the air is going to be forced in under pressure. You may have leaking pipes. So a lot of times when we talk about too much nitrogen gas, it's because of a mechanical failure in some of these systems. There are other causes for that, but usually with the systems you guys are going to be dealing with, it's more of a problem with some sort of a mechanical failure or a design problem. All right, so we talked about degasification, solids capture. So that's essentially removing all the crap that's floating around in the water that you can see. It's kind of like, basically we're talking about filtering out all of that. And again, you guys are going to be using these bubble bead filters, which actually do two things, but we'll talk about solids capture. So these are going to be units. Your water is going to flow from, I believe, top to bottom, and then they're going to be filtering out all the particulates in the water. So we talked about the biofilter and how the two groups of bacteria are breaking ammonia to nitrite and then to nitrate, in addition to the plants using the ammonia and nitrate. And where most of that is going to be happening is also in these filters. So these bubble bead filters do two things. They act as your primary biofilter as well as your primary mechanical or your solids capture filter as well. So I know this is probably thinking a bit too far ahead, but if you think about it, you're going to have this building up a lot of crap in it. So if there's too much crap in it, the bacteria are not going to be able to work as efficiently. And that's why you're going to have to manage how often you backwash it or clean it. So, there's bacteria that are trying to do their work with ammonia, and then you have the filter trying to get rid of all of the feces and other materials in the water. And they're going to start blocking the bacteria that you want to be in there, the bacteria that are doing the ammonia, doing all the work against ammonia. Of course, with the particulates, there are other bacteria that are attached to them, and so they're going to be competing. So that's kind of why how you manage the bubble bead filter is really important for both your solids capture as well as for your biofiltration or for removal of the ammonia. So that's doing both. Again, circulation, think about it as kind of, I made that analogy, your ammonia, after you break down protein in your body, the ammonia goes into your blood, goes to your liver. So essentially your heart is kind of like the pump and the pipes are like your blood vessel is kind of going through, but you're trying to essentially make sure that the water is circulating and going through all the different units of filtration so that each different part of the filter can do its job. And again, some of these filters are combined, like the biofilter and the solids capture filter with your bubble bead. And again, as you guys, I believe you're going to have this plant fixed bed, or you're in your aquaponics type systems. So just to remind you, plants do use ammonia and nitrate, so they will help with your handling of the ammonia nitrogen cycle. But remember that in the light, they will actually decrease this carbon dioxide levels. Plants use carbon dioxide and increase oxygen levels. But in the dark, they are going to actually use oxygen even more than they produce it. And they are going to be also breathing or respiring carbon dioxide. So there is a difference as well with light and dark cycles when you're dealing with plants. So they're not only being good, they can also be kind of bad in the evening for your system. So keep that in mind as well. So, sure, yeah.
Do you recommend keeping it UV light on the plants then?
I don't know. I mean, I think you probably just need to manage it and keep an eye on it. I mean, I'm assuming, and again, I'm not a plant guy, that they probably do need a dark cycle to a degree, but that would be, more of a aquaponics section. I think just keep an eye on your system. It should probably be fine. Yeah. So again, we talked a little bit about theory, and then we got your system there. And so just to reiterate what you got going on here, so you've got your plant bed, which does do some aeration and biofiltration. Your bubble bead filter is going to do the biofiltration and solids capture. Your pumps and pipe are helping with the circulation of the water in order to do the different things that need to be done. You've got an air pump and a tubing with an air stone that is going to be your aeration. So what is missing here? Which part did we talk about is missing? I think I made a reference to that you guys would be building one maybe later. Exactly, yeah, degasification, because you're going to have issues with the carbon dioxide as well as lower oxygen. This will help with that as well, even though you do have aeration. So degasification, again, Eric, I talked to him about it, and he said a lot of times that's sort of a project that you guys can do with your students is build a simple degasification unit for these systems. All right, so hopefully you guys understand a little better all these different components that we talked about. And you know, Debbie and Eric and Tatiana are going to go over some of the different testing kits. I included, and again, you guys are going to have a copy of this, kind of some general suggested good levels for warm water fish with regard to these different parameters. Again, you may see different numbers, but this kind of will at least give you some sort of a guideline on things to consider. And remember, with salinity, again, that's typically it's not something you're going to want in a tank that, I mean, a system that has plants in it, but I just included kind of fish only there. So this is kind of a really
right now, that's why the printer is running. I meant to have paper copies, and then we forgot the printer broke, and then whatever. So we're printing it out right now.
Oh, okay, yeah, you guys will get a copy. Don't worry.
4 different copies of all these presentations. Just a reminder.
Yeah. So this is just a really quick kind of like talking a little bit about what we talked about in one quick slide. So hopefully that'll help you remember everything that we discussed. You got ammonia, the different types of bacteria that break it down into nitrate. The bacteria need oxygen and bicarbonate, or your alkalinity. They're going to produce CO2 and make the water a little more acid. And then the nitrate is going to be removed either by dilution, water changes, or by the plants. And the ammonia also can be used by the plants. So a little bit of a quick rundown. So now common system problems. There are a lot of things that can go wrong. And these are just a few of the things I want to kind of talk about with you. So new tank syndrome. And I put new in quotes, and as well as you'll see there's an old tank syndrome in quotes that we'll talk about. So new tank syndrome typically means that the biofilter, all the bacteria are not high enough in number to handle the load that you're giving it. So it's really common for folks that have aquaria for the first time to want to put as many fish as possible. You know, again, I'm talking about like a hobbyist, like a pet store. So, you know, they'll buy a 10-gallon tank, and then they'll buy, you know, get 10 or 15 fish, put them in. And now that you guys hopefully understand, there's not enough of those bacteria that are actually going to be able to handle the ammonia that they're going to be making. And that's typically why they die after maybe a week or so, because they're being fed protein, the protein's breaking down into ammonia, as well as the amino acids that the fish is using. The ammonia is going into the water, it's building up, and the ammonia is essentially hurting the fish externally as well as internally. So too many fish, biofilter, not enough bacteria, that's going to cause either really high ammonia levels or nitrite levels, depending on where in that cycling process the system is. So that's something that usually I think you guys would be doing. You'd be monitoring your ammonia and nitrite levels to see when you actually have your ammonia go up and down, and then your nitrites up and down, which ideally will be when your system is kind of seasoned or cycled. So again, you can also have too many fish. You can have overfeeding, a lot of things that can cause that. Old tank syndrome, I put in quotes as well. And Debbie brought up a great point. We call it old tank because traditionally we think about this as like this happens over a really long period of time. But hopefully you guys saw, or we talked a little bit about and hinted at the fact that alkalinity or the buffer, especially the bicarbonate, is really critical. So when we talked about water source, we talked about differences among surface water, municipal water, well water, but they're also going to have a lot of, obviously a lot of different parameters. There may be water sources that have a very low alkalinity, and because the bacteria need that alkalinity as part of their process, if you start with your source water having low alkalinity, you can see that they're going to use it up really fast, and you're going to have problems with pH, et cetera, as well as the biofilter. So old tank syndrome typically is going to be problems. Maybe there's not enough water exchange to help increase the amount of bicarbonate or buffer from your source water, because the system has been set up for a long time and no one's been watching that buffer. Or you can have really, really high densities of fish and feeding a lot, which is sort of similar to a little bit to new tank syndrome, except that the tank was at one point cycled. So the bacteria were working together, but then suddenly somebody decided to feed more, or the fish are getting bigger and bigger. And so they're going to need more food. And what happens again is that alkalinity is going to be used up. and the buffer capacity of the water is no longer going to be able to handle the acid that's being produced by the water. So what happens in terms of what you're going to see is you're going to have a drop in pH. And that's kind of why we always say you really want to know your baseline water source. You want to know what you're starting with so that you can kind of monitor what happens over time. Your alkalinity, as we talked about, your bicarbonate is going to get used up as the pH drops. If you have too much carbon dioxide and you're not degassing it with the degasification unit adequately, you're going to have the CO2 also adding to acid to the pH dropping. And one important thing, besides the fish not being happy as the pH goes lower and lower and lower, is that the biofilter bacteria we talked about, the AOBs and the NOBs, the ammonia oxidizing and the nitrite oxidizing bacteria, prefer to work at a pH of about 7 to 8, maybe a little over 8. So as your pH gets below 7, the bacteria are not also going to be working as efficiently as possible. So there's a lot of reasons why you really want to monitor many of these parameters over time. And it's not just the fish, it's also the biofilter. Normally what's going to happen then, big issue, you're going to see a huge spike in your ammonia, and I didn't mention, well, I did, and a huge drop in pH. So one story I like to tell is I did have an aquarium when I used to work at a fish farm, and we could get whatever fish we wanted. I remember it was set up with really nice rainbow fish. If you're familiar with that, it was a planted tank. I bought a really nice African cichlid, put it in the tank, it like dropped to the bottom immediately. And I thought, no, everything looks okay. But you know, obviously something was wrong with the fish. And then I checked I think I checked my ammonia and nitrite. And just like your aquaponics system, they were actually 0. And I think it's probably because the plants were using the ammonia and the nitrate, or the ammonia as well as the nitrate, if there was any left. But then I went finally and checked the pH, and my pH had dropped from 8 to 4. So that was why. So the other fish were kind of had gotten used to that pH. They acclimated to it. They were probably not going to last much longer, but they had acclimated. The African cichlid was at a pH of 8 when I brought it from the farm, stuck in a pH of 4, and was not happy at all. So that was, yeah, my extreme example of old tank syndrome that actually does happen. So fixing problems, again, this is kind of a common sense sort of slide, but you really, you know, obviously maybe early on for some of you may want to get help from more experienced people, definitely from us and Eric, or more experienced aquaculturists or folks that you heard yesterday that have systems, you know, in production right now. You want to be really careful and thoughtful and not knee-jerk and start doing things without having any idea why, you know, what's going on. You really, really want to want to know what parameters are bad and why. And it's really, again, all of the parameters are fairly important, and you really want to know. You want to have a regular testing program. You want to have good reagents as well as good other tools. You know, if you can get an oxygen meter, et cetera. Really have good system management and protocols for you and your students to follow to make sure everyone's doing things at the way they're supposed to. Really good records as well. The things that are going to kill your fish the fastest are oxygen, issues with temperature, pH, rise in toxic ammonia, or too much nitrogen gas. I mean, again, a lot of other things can kill your fish fast, including bacterial diseases, parasites, et cetera. So, you know, the infection type diseases are an issue, but really water quality diseases are one of the things people don't really think about a lot, or maybe ignore, and can lead to really, really quick mortalities. So those are really critical. Depending on what the issue is, you may have to do slow or rapid water changes. If you have high ammonia and your pH is really low, if you guys try to do too much of a water change, what's going to happen is your pH will go up, but you're not getting rid of enough ammonia. So you're going to have more unionized or toxic ammonia. If you guys know, we talked about the fact that, you know, the amount of toxic ammonia goes up a lot faster as the pH goes up or increases. So again, you really need to know what's wrong before you correct it. You may have to add alkalinity or buffer. Some people will add like baking soda, et cetera. There's different ways to handle buffer. Other types of buffer you can add as well, but you got to be careful and know how you're doing it. You may have to just do things like increase your aeration or build a degasification unit if you don't have one for handling your oxygen, carbon dioxide. And it actually does help with nitrogen gas too. If you've just got a small amount that's a little too much, it'll help relieve that. Obviously fixing pumps, pipes, anything that's going wrong mechanically, and making sure you're cleaning and backwashing appropriately as well. So again, I know the lab to follow, these guys are going to talk about things. There's a lot of really important parameters we discussed. Hopefully you at least get a kind of feel for it. If you don't necessarily understand it completely, you're going to have a copy of this, and obviously us as well to ask more questions about in the future. So that's all I had. You guys have any questions at all? Sure.
Do the AOBs and NOBs interact in any kind of way, interfere with each other
During
that development?
That's actually a good question in what I guess in a way, because one thing that does happen is if you have in terms of ammonia or nitrite, if it's too high, if the ammonia gets too high, your NOBs or AOBs may be inhibited. So there is kind of a, with regard to the ammonia or nitrite levels, there is some of that. Now, in terms of the bacteria themselves, I think it may be, they're going to be in the biofilter, in the B filter. So there's going to be maybe some space interactions. They're like, who gets more space. One thing I do want to mention, and we talk about biofilms, or if you guys are familiar with kind of like scum on the surface of things, that's a biofilm. So believe it or not, these bacteria are actually going to be growing in your pipes, as well as on the sides of the tank. Anywhere that there's going to be potentially a scum, you can get these bacteria on it. But most of them are going to be in that bubble B filter. So you actually do have other areas where these bacteria can do their work, but the bulk of them are going to be in that B filter.
Also in the aquaponics system.
And
there'll be lots of surface area.
Yeah, exactly. Good point. And the plants are going to be using the stuff as well. So
how long does it take to start a biofilter? 6 to 10 weeks. Thank you.
yeah. So
I got the printout just in time. Yeah, my apologies on the oversight on not having the right computer for y'all.
So well, but and she's right. But again, it really depends on how you start your system, and you can buy
Too
bacteria.
much wiggle room.
Yeah.
6 to 10 weeks.
Well,
Hammer in 6 to 10 weeks.
All right. 6 to 10 weeks. But I would say, but more importantly, is that you actually monitor your
Yep.
water parameters.
We're gonna
Yeah.
see that.
Yeah, exactly. Yep.
No, watch your graphs. We're gonna talk about that tomorrow.
There's going to be a lot of detritus and other things in there that will be producing CO2 because they're going to be respiring. We've got other bacteria in there. So it may change a little bit, but ideally it will help kind of increase or mitigate any drops in pH, because a lot of those things in there are actually going to be decreasing your pH over time. But again, hopefully you're going to be on a schedule. She said you guys will talk more about that in general. But yeah, bottom line, she's right. Don't go too fast, but you need to monitor your water quality parameters, because that's really the only way to know what's going on. Yep.
Just a little bit of experience with my kids in my tanks. When they see that the pH has changed, they immediately want to fix it and solve the problem. And they will go to grab like a chemical like this that's pH up or pH down, right?
Right.
And they'll add like 3, 4, 5, 10.
Yeah.
Even though it's a 20-gallon tank.
Right.
Fish plummet because they can handle very small changes in pH over time, but rapid will kill them.
It's
Yeah.
the product of oil.
Right, so what I tell them, but what this is for you guys to know, which is a kind of bit cheaper, and you can speak more on this, if it's good or bad. They can add like limestone rock, like 1 or 2 little limestone rocks, will buffer the water slower than adding any chemicals.
Right, exactly. That was why I said additional, sodium bicarb is good, but yeah, we use things like agricultural lye, dolomite. Again, I don't know how you guys are setting up your systems, but those are kind of a slow release. They will actually add hardness as well to your system. So there's, again, you just got to know what you're worried about and how to fix it. But a lot of it really does go to, for you guys at the outset, kind of just getting a feel for what your water starting is, and then monitoring and tracking how quickly the parameters change. But yeah, you're right. Dolomite, limestone, those things will help buffer much slower. Yeah.
And on that note, that might be a good, once you guys get your baselines, you can come up with a plan. Like you guys can start thinking about how that's going to affect your water parameters and everything like that when you do water changes over time, blah, blah, blah. And if you have questions about, hey, how is this going to affect me, reach out. We'll talk to you about it.
And we got even one more twist, and Eric probably may have mentioned it, but he's been going around and he's got a project looking at different wells throughout the state. And the wells will actually change over time as well, seasonally, as well as I think year to year. So if you're using a well or a deep well for your source, you may actually have changes in your starting water. So it's always good to know, and test your source water periodically just to see if things have changed a bit.
Any other questions? Awesome, thank you so much.
No problem. You guys are ahead of schedule, so.